You should have waited until after the break to grade those tests, but that's okay. Now look, this is important. I just want to talk about, have you ever heard of Boyle's charge or Gay-Lussac's law of gases? No? Okay. Let me explain, okay? There are three laws that all gases adhere to at what I call normal conditions. Normal conditions are conditions that are lifelike to me. Understood? In other words, what temperature does most of the world live in? It lives between 0 degrees Celsius and 40 degrees Celsius, right? That's what the world lives. That's how the world lives. Let's go crazy and say negative 50 degrees Celsius to 100 degrees Celsius. But the world certainly lives within that range, correct? Okay. Well, within that small range of conditions, gases behave ideally. Is that running? Gases behave ideally. In other words, let's say your chlorine gas, Eden, your oxygen gas, Munkel, your nitrogen gas, and I'm oxygen gas, right? Okay? I have as oxygen gas, O2. What are you? CO2. What is it? O2, N2, and what am I? I'm oxygen, what are you? We're both oxygen. Okay, we're both oxygen, okay. Together, you and I, Eden, have a half a mole of molecules, right? Together, right? Half, so 3.01 times 10 to the 23rd, right? You have a quarter mole of molecules, your chlorine, and your nitrogen, you have a quarter mole of molecules, right? So together we make up 1 mole of molecules, correct? Yes? Well, the fact that I'm oxygen, you're chlorine, you're nitrogen, Eden, you're also oxygen, is irrelevant. The difference in the chemistry of the molecules is irrelevant because they're all going to act, all those gases are going to act the same. Matter of fact, if you add up all of those particles, and let's say the conditions are STP, 0 degrees Celsius, 1 atmosphere, or 100 kilopascals, the volume is going to be 22.4. So we're going to act ideally. Correct? We're going to act ideally. Yes? Now, if you create very cold temperatures, those cold temperatures are going to do what? What are they going to do to the molecules? They're going to force them together, correct? Yes? They're going to force them closer together. What happens if I increase the pressure on those molecules? I'm not talking about by 1 atmosphere of pressure. I'm talking about 10, 15 atmospheres of pressure. What are you going to do to the molecules? You're going to do what? They're going to get close together. As they get closer together, they're going to realize, wait a second, I'm an oxygen and you're a chlorine. What am I doing with a chlorine? Now I know your identity and you know my identity. I know his identity. All of a sudden they're going to be close enough where they're going to start acting like individual molecules because they're individual molecules from unique elements, correct? So at extraordinary conditions, those gases are going to start to act as if they're real gases. Real meaning chemically unique, okay? If I take a liter of water, you ready? My left hand, a liter of water. In my right hand, I take a liter of alcohol, ethyl alcohol, right? And I close the top up and I put in a straw. And that straw is this long. So here's my bottle, and up top is a straw, okay? Shall I draw it? Where can I draw it? Can I draw it here? Can you see over here? Okay, so I have a bottle. All right, it's not a great bottle. Okay, let's draw a better bottle. Okay, Let's draw a better bottle. Okay, that's H2O. That's ethyl alcohol. Okay? You okay? Same exact volume. Same exact volume. Now, I have a straw coming out of here. Right? And that straw has a certain mark, okay? This is liquid, this is air, right? Same temperature, right? Let's say it's room temperature. Let's say it's 20 degrees Celsius. Okay? Let's say it's 20 degrees Celsius. If I heat these two bottles 5 degrees, let's say, right? One is going to expand up to here, and the other one's only going to expand, they're going to expand differently. Right? Aren't they? They're going to expand differently. Why? Because those particles are very close together. They have physical properties that are unique for that chemical. They have physical properties that are unique for the fact that they're ethanol, and physical properties that are unique for water because they're so close together. Correct? Yes? If I did this for a gas, let's say this is O2, this is Cl2, and I heated it, it would go the same. Under regular conditions, normal conditions, they would go the same. How about if I put them under tremendous pressure? They would start to act like liquids, wouldn't they? They would start to act uniquely, wouldn't they? So all of a sudden, this way, they may be different. Not as different as water, possibly, but they would start to act uniquely. Correct? If I take any gas at normal conditions, and I subject it to a battery of tests, volume, temperature, pressure tests, the gases all respond the same. Oxygen, nitrogen, chlorine, fluorine, they all act the same. If it's a gas, it reacts the same to those environmental conditions, change in volume because of pressure, whatever. Let's look at Boyle's law. This is called Boyle's law. Boyle, Robert Boyle. He saw that if a house falls on your face, what's going to happen to your head? It's going to go, okay, that's kind of a silly example, but if I take a balloon and I subject it to tremendous pressure, what's going to happen to the volume of the balloon? Is it going to increase or decrease its volume? It'll decrease its volume, isn't that correct? You know that though, right? I mean, you knew that before you came in here, right? Yeah. So if I double the pressure, I'm going to have the volume. And that's what this is. They're inversely related. They're indirect. You increase the pressure, you decrease the volume. That's why it's a product constant, because it's not linear. You see that? It's not linear. You see that? In other words, it's xy equals xy. This equals a constant. So any point on here, this would be P1, V1, this would be P2, V2. They're equal. The product of them are equal. You see that? Because they're on the same line. Why do I have three lines here? Different temperature. At constant temperature, this line represents constant temperature. So at constant temperature, I take a volume and a pressure, and the product equals a constant, right? So if the product equals a constant, let's say xy equals a constant, what would happen? Y equals c over x. Does that look familiar? Y equals 1 over x. Isn't that the graph for y equals 1 over x? Isn't it? A product constant represents a nonlinear relationship, an indirect relationship. Do you see that? Yes or no? Okay. Sorry, I got this backwards. Actually, it was Gay-Lussac who gave Charles the credit for a law. This is Gay-Lussac. This is Charles. Gay-Lussac made sure that Charles got the credit for that law. But the same thing is true with pressure and temperature. Let's say you heat a can of beans on top of the stove. What's going to happen to the pressure inside the can of beans? It's going to get high, right? Any gas, let's say there's gas inside that can of beans, not beans. What's going to happen to the pressure inside that can as you heat it on top of the stove? It's going to get tremendous, isn't it? Because this is constant temperature. This is constant temperature. This is constant volume, right? The can, constant volume. And this one is constant pressure. In other words, I run this experiment in a laboratory. I take a balloon. A magic balloon that's not going to, it's not really magic, but it's not going to melt or anything. I take a balloon, it has a certain volume. Can you see the balloon? I put it in an oven and I turn up the temperature. What's going to happen to the volume of the balloon? It's going to increase, right? That's why it's a quotient. As I increase this, I have to increase this, don't I? Right? Because it's linear, isn't it? Y over x. Y over x. I am controlling the temperature, aren't I? You get that? As I increase the temperature and the volume, temperature in this experiment is independent, isn't it? Pressure, temperature here is also independent because I have the can on top of the stove, don't I? This is Gay-Lussac's law, this is Charles' law. Do you see that? Yes or no? Yes. So we're establishing right now that the relationship between pressure and volume is indirect, between pressure and temperature is direct, and between volume and temperature it is also direct. Do you understand? Am I being clear? All right, now. So if I want to combine these laws, I can do it here. PV over T equals PV over T. Well, where did I get that? Well, if pressure is constant, wouldn't that drop out? If it's the same number on both sides, right? So if pressure drops out, it's V over T equals V over T. That is going to be Charles' law. If volume is constant, it's P over T, P over T. That is going to be Gay-Lussac's law. If temperature is constant, it's going to be PV equals PV. That's Boyle's law. This is the combined gas law, because maybe things are changing at the same time. For instance, I have 1 mole of gas at standard temperature and pressure. I know what my volume is, it's 22.4 liters, correct? Right? 22.4 liters. I know what my pressure is, it's 100 kilopascals. I know what my temperature is, 0 degrees Celsius. But you never use, in gas laws, you never use Celsius. What do you use? Kelvin. You add 273, right? Correct?
And to get to Celsius, you have to
Subtract 273, correct? So let's say this is going to be 100 kilopascals. That's going to be 22.4, and that's going to be 273. Well, what happens if I say, okay, well, what's my new volume if I have a higher pressure and a higher temperature? What's my new volume? I've got to calculate it. So I'm going to say 2 atmospheres of pressure, or 200 kilopascals. I'm going to say 373 Kelvin, and I want to know the volume. So you have all 3 changing. This is called the ideal gas law. I'm not going to be comparing gases, I'm going to be given a gas. This is pressure and volume. You see how they're inversely proportionate because they're together? So this makes sense, doesn't it? If I solve through for volume, I see that it's P over T. If I solve through for pressure, I see that it's T over V. So the relationships are the same, aren't they? But this is moles. N is moles. This is the ideal gas constant. Clear? And we're going to work on this when we come back from break. All right? We come back from break, it's day 4, so we're going to do a lot of work. We're going to absolutely go crazy the day we come back from break. Does it make sense? I just wanted to give you an idea of how gases are going to fit into this. We've already done gases in a sense, haven't we? Because we've done volume. But this is important. What did I do? I showed you that within a certain framework of conditions, gases act as an ideal. What do I mean ideal? In other words, they all act the same. They don't realize they're chemically unique. But as I have extraordinary conditions, they react real, as if they are chemically unique, as liquids do. Correct? And then I had to show you the relationship between changes of pressure, volume, and temperature, and gave you credit for those scientists. Understood? Now, have a great break. Enjoy your water festival. Celebrate the end of the rainy season. It's been a long season. And have a good weekend.